Now we're going to see constructive and destructive interference as an introduction, and here maybe we could cover the double-slit experiment made by Young. So we have one wave, f, is equal to cosine of kx minus omega t, and g is cosine of kx minus omega t plus p. This is the phase. This is what we call the phase. These waves have the same frequency, the same speed, the same wavelength, because wavelength is 2 pi over k. We have here the same k. Frequency is 2 pi f is omega. We have the same omega, we will have the same frequency. And the same speed of propagation, the speed is omega over k. The only thing is that they could be in phase or out of phase. That would depend on this term. In this example, we have something called destructive interference, because if we add them, we could see, we see that G is the negative of F, because it is out of phase 180 degrees or phi. So it's completely out of phase. So G is equal to the negative of F. So if we add them, G plus F is the same as negative F plus F, so it is 0. So we have completely destructive interference. So here we have destructive interference. For constructive interference, let's say that here instead of having a P, we have a 2P. So the G and F, when we add them, it is positive additive. For example, if we have the amplitude A here, the new amplitude would be 2A. So that would be constructive interference. So in order to have constructive interference, we need a even integer of pi. Could be 2 pi, 4 pi, 6 pi. And to have destructive interference, we need a odd integer of pi. So let's say that for constructive interference, we need, for destructive interference, we need that the phase be, let's say, first for constructive interference. For constructive interference, we will say that the phase needs to be a even integer of pi, so n to n pi. This would certainly make a even integer of pi. And so the destructive interference, we need a odd integer of pi. So it would be it would be 2m plus 1 and then times pi. So these are the conditions to have constructive and destructive interference. So now we do the double-slit experiment. Oh, I erased the waves. Well, anyway. So we have a screen. Here we have a screen. We have two apertures. The one aperture. And this is the other aperture. The distance here is called D. And we are shining light. The angle from the center, let's say here we have, let me do it in green. This is the center. So we are shining light. The angle from the center to any point here, that is theta. And because if this length, let's say that the screen is very far away, so this is length L. If L is much larger than D, I know that it is not drawn to scale, but if L is much larger than D, we will have quite parallel lines for this aperture and this aperture. So we have this, we can translate this also to here. Oh, it does not look too much patterns. Let me do it again. Yeah, something like that. Something like that. All this is theta. This is theta. It's quite the same. So theta would be very small, and we could use the small angle approximation. Remember, in small angle approximation, sine theta is approximately theta, and tangent theta is approximately theta. So, the waves, here we are shining light, and we have the wave propagation. We have, you can see it, you can view it as two sources of wave with the same frequency, same speed of propagation, same wavelength. At a given time, let's see t, the waves have traveled different length in the path. For example, this at some time, the wave here, this source, the wave traveled this distance, for example, this distance or this distance, and the other wave traveled this distance at that time. We see a here it's not seen quite well, but we see this is the difference in the path being traveled by the waves. Let me call that, if I call this R1 and R2, I have this, I will call it R2 minus R1. Sometimes this is called delta X, but I don't want to use delta X because other people use this. In this case, is vertical distance, as I'm putting it here. This looks like vertical distance, but sometimes this is called X. So I don't want to confuse X here and the X in other direction. So I will call it R2 minus R1. Alright. So we have these phases. Something I forgot to do is we have cosine of kx minus omega t, and cosine of kx minus omega t plus the phase. And when we add here we have a phase. That phase, that is the pi or 2 pi or whatever we were talking about, will produce a difference in the path traveled. So this, let's say this is G and this is F. They have the same frequency, the same speed of propagation, but this wave traveled a different distance than this wave. That is because, let's say that let me call this R2 minus R1 delta R. Yeah, delta R. So we have cosine of k x plus delta R minus omega t. So this is the same as cosine of kx minus omega t plus k delta R. So we see that this wave has a phase of k delta R. So the phase is k delta R. Yeah, that's the phase. So this is delta R, and depending on exactly the phase, that is, we cannot change the k, we can only change the R, but we would see that we can have constructive or destructive interference. So now that we know that, let me make a little geometry for the angles. I will draw a line that will be perpendicular to these lines. So could be something perpendicular. I think something like this. Yeah, like that. Yeah, like that. So oh, it's not very drawn to scale. Here, actually, let me draw it. Bear the angle up. This is theta. That is theta. All this is 90 degree. Oh, sorry. All that is 180 degrees. This 90 degree angle, and this is 90 degree angle. So we have that this one, just this one, that one is 90 minus theta. On the other hand, let's say now we want to know this angle. This is the difference in the path travel, so I want to know this angle theta. So I have that this is also 90. If you want, we can project this more like this until you can see it as all this angle here. So this is 90. This is 90 degree angle. This is 90 degree angle. This is 90 degree angle. So here I have theta. And I have that this theta, or this angle, would be the same as that theta. Be careful, here we don't have 90 degree angle. No, this is not 90 degree angle. The 90 degree angle is with this line. Sorry, I mean that here we have 90 degree angle, but not this one and the black one. No, is the two greens, or I think that I should have drawn it in purple. Here we have 90 degree angle. So here we have theta. Alright, so now that we have theta, yeah, tangent, sine of theta. Sine of theta is this distance, dr, divided by this is the hypotenuse. This r is the hypotenuse. This distance is the hypotenuse. Sorry, I want to do it with this. Yes, this triangle. So this is the delta r. Sorry, delta r. And what is this? This is d. I noticed my triangle is not drawn to scale, but I should have drawn it all this way. So this is sine theta, and by this small angular approximation, you could say that theta is dr over d. dr over d. Alright. And what is the tangent of theta? Tangent of theta would be x over L. Alright. So sorry, tangent of theta. But because tangent of theta is approximately theta by the small angular approximation, you could say that theta is x over L. Okay. Yeah. So x is equal to theta times L, and so x is equal to 2 delta R over D times L. Now, in order to have constructive interference, we need this condition. This condition. So we need that the phase be 2 pi R. That would be the phase. So, in order to find the maxima and minima, we need to set up this equation when we have the constructive interference and destructive interference. So 2 m pi needs to be equal to here. So k, you can see it here. Yes, so k delta R is equal to 2 m pi, or delta R is equal to 2 m pi over k. 2 pi over k is lambda, so the R is equal to m lambda. So when R2 minus R1, the difference in the path traveled by one way and the other way is an integer of lambda, we would have constructive interference. On the other hand, for destructive interference, we have k delta R is equal to 2m plus 1 times pi. So the R is, and let me do it here in order to see it. The R, oh, I don't know if you can see it. Yeah, so the R is equal to 2m plus 1 pi divided by k. 2 pi over k is lambda, so here I have m lambda, and pi over k is half lambda. So for destructive interference, I would have that the R is equal to m plus 1 half lambda, or you can also put it as 2m plus 1 lambda divided by 2. So m can take any value. So for constructive interference, here constructive interference is the R is equal to m lambda. So for constructive interference, we have 3 lambda, 2 lambda, 50 lambda, and for destructive interference, we have half integers of lambda, because if m is 1, you would have 3 halves of lambda. If m is 5, you would have 11 halves of lambda. So now this is because now x for constructive interference, would be m would be tangent, yeah, I did right. X, sorry, here I mixed it up. X is equal to theta, sorry, yeah, x is equal to theta times lambda, yeah, so theta first. So theta is m lambda over d, and here theta is 2m plus 1 lambda over 2. So x here, this x that is we have tangent of theta is x divided by L. If we want x, we have theta times L. So x is equal to m lambda L over d. And for destructive interference, we have x is equal to 2m plus 1 lambda over 2 times L, and then over d. Alright, so that means that, certainly you know that when we have destructive interference in the wall, we will see it as black bands, and in constructive interference, we could see it as white bands. When we see white bands, we call it maxima. When we see black bands, we call them minima. When we see white bands, we call them nodes, and when we see black bands, we call them antinodes. So the difference between a node and another node could be again have lambda, and the difference between a antinode and a antinode is half lambda, and the difference between the difference between a node and the antinode, or antinode and the node, is half lambda. The difference between, or the distance between, here the distance between two nodes or between two antinodes is lambda, quite the same as when we talk about musical instruments and the waves for nodes and antinodes. So when we have that this x, measure here from the center, when this x is m lambda L over t, let's say m is 1, we would see at this point, if this point x is that, so m lambda L over t, we would see white band, and here we would see a constructive interference. If at this point we have that x is equal to 2m plus 1 over t lambda L over 2, we have destructive interference, and we will see black band. So this is a antinode, this is a node, this is a minima, this is a maxima. And so you have these parallel lines, alternating minima and maxima. So the distance between minima and maxima is just half lambda. Between two maxima would be lambda, between m equals 1 and m equals 2. The difference between two minima would be again lambda. So now in the next video we will discuss the single slit experiment.